Lab 2, Motion of a Falling Object. The objective of this lab was to observe the motion of an object that is dropped from rest and falls somewhat slowly and straight down in order to observe the interactions of gravity and drag force with the object. The object used in this experiment was a crumpled sheet of printer paper. In this lab, tracker was used to extract the position and time data from the observed motion to construct two computational models in V idle based on Newton's second law to show the net force acting on the crumpled paper. The first model significantly overpredicts the crumpled paper's position. The second model yields a better fit and prediction of the actual position and time of the crumpled paper. The applicable fundamental principle acting in the observed motion is Newton's second law, which reveals to us that an object's final velocity can be found by adding its initial velocity to the sum of all the forces acting on that object divided by that object's mass multiplied by the change in time. When the net force acting on an object is non-zero, an object's velocity will change with respect to time. In the first model, we choose the net force to strictly be the gravitational interaction between the crumpled paper and the Earth. In the second model, we choose the net force to more accurately be the sum of gravitational force and the drag due to the interaction between the crumpled paper and air. The drag force acts in the opposite direction of the object's motion. In this lab, the Earth is pulling down on the object with a constant gravitational force, while air is increasingly pushing up on the object until drag force equals gravitational force when the object reaches its terminal velocity. The net force acting on the object then becomes zero, making the final velocities become equal to the initial velocities, making velocity become and remain constant until the object experiences a non-zero net force again when it interacts with another object in its surroundings other than the air and the Earth. Here is the video of the observed motion where the crumpled sheet of paper is the system and everything else is the surroundings. The origin is located at the center of the paper at the beginning of the video. Downwards is set to be the negative y direction. The coordinate axes are tilted slightly due to the motion being recorded at an angle and to account for the slight right movement of the crumpled paper. Here we are only concerned with the object's movement in the y direction. In the first portion of the graph of the paper's position versus time, where the graph is curved, the object's velocity is changing with respect to time. In the second portion of the graph, where the line is straight, the crumpled paper's velocity is constant because the net force acting on the object became zero. This is where the object has reached its terminal velocity. Here are the initial conditions put in VPython from Tracker in order to calculate the net force. Delta T is set to be 0.001, which is a good choice based on the total duration of observation. The final time of observation is taken from Tracker and set to be the limit of the while loop where all the iterative physics calculations occur. The while loop contains the fundamental principle of Newton's second law. For further detail and explanation, refer to Lab 1. When we run the model that only accounts for the gravity, we see this. The yellow arrow is a representation of the constant gravitational interaction acting on the crumpled paper. When we compare the experimental data versus the computational model predictions, we see that this model, which only accounts for gravitational force, significantly overpredicts the object's position versus time. The reason for this discrepancy is because gravity isn't the only interaction the object is experiencing. The object is also experiencing the interaction we discussed earlier, drag force. This is how we calculate drag force. The constant B was found empirically by using the final position data from Tracker. Here's where all the information for drag force was input into VPython. When we run this model that accounts for both gravity and drag, we see this. At first, the only arrow we see is the yellow arrow representing gravity. Then we see the blue arrow appear and begin to grow, which represents a drag. The blue arrow approaches the sides of the yellow arrow in the opposite direction, showing the object approaching its terminal velocity. When we compare the experimental data versus the model data, we see that this new model, which accounts for gravity and drag, is much more accurate than the model which only accounts for gravity. There is still some discrepancy between the new model and the extracted data from Tracker, possibly due to error in accurately recording and tracking the object's position. When examining the velocity versus time in the first model without drag, we see that velocity continues to change with time as the net force continues to be non-zero and constant. When examining the velocity versus time in the second model, the one that accounts for gravity and drag, we see that the velocity changes with time during the first portion of the observation, but then becomes constant at the end of the observation, showing that the object reaches its terminal velocity. What if the object were thrown downward with an initial speed of 20 meters per second, the terminal velocity would still be the same for the crumpled paper because terminal velocity only depends on mass, surface area, and density of the crumpled paper, and none of those properties have changed. This can also be confirmed by printing the final time and velocities of both scenarios and comparing them.